All right, today we're going to jump into a question that sounds pretty simple on the surface, but is actually really deep. How do you measure the exact length of a curve? We're going to unravel the whole concept of arc length, which is just a fundamental, super powerful tool in calculus that lets us do exactly that. So let's get right to it. So here's the game plan. We'll start with the big idea, what arc length even is. Then we'll build the formula from scratch. After that, I'm going to give you a super clear 5-step process that you can use every single time. We'll test it out on a basic curve, and then we'll level up with some trickier examples, the kind you're probably going to see on an exam. And finally, we'll wrap up by talking about why this whole concept is just so important. So let's start with a really basic question. We can all measure a straight line, right? But what about a curve? How would you find the precise length of a winding road or the track of a roller coaster? This is the exact problem that arc length was invented to solve. You can think of it like this. You already know the distance formula from geometry, which gives you that as the crow flies straight line path between 2 points. Arc length is different. It gives you the actual distance you'd cover if you were walking along the curve itself. Okay, so how does this actually work? Well, the big idea behind it is just a beautiful piece of calculus intuition. Just imagine zooming way, way in on any smooth curve. If you zoom in far enough, any tiny little piece of it starts to look almost perfectly straight. And the absolute magic of calculus is that it lets us add up an infinite number of these tiny, infinitely small straight lines to find the total length of the whole curve. And that idea, that core concept of tiny little straight lines, is exactly how we're going to build the formula. We're going to start with some simple geometry you already know and turn it into a seriously powerful calculus tool. So let's call the length of one of those teeny tiny segments ds. We can picture this tiny segment as the hypotenuse of a tiny little right triangle, where the other two sides are a tiny change in x, which we call dx, and a tiny change in y, called dy. And hey, if we've got a right triangle, we know what to do, right? The good old Pythagorean theorem. So the length of our tiny segment squared, ds squared, is just dx squared plus dy squared. And if we take the square root of both sides, we get the length of that one tiny piece of our curve. Now here's the key move. This is the algebraic trick that turns this from a geometry idea into a calculus problem. We're going to do a little manipulation. We're going to factor a dx squared out from under that square root. Now, why on earth would we do that? Because when we pull it out of the square root, it becomes just dx. And look what we're left with inside. dy dx. That's the derivative. And that dx on the outside is exactly what we need to set up our integral. And this brings us right to the final formula. The total length, L, is just the integral, which is really just a fancy sum of all those tiny ds segments from our starting point A to our end point B. This is it. This is the formula you've got to know. Just a quick but really important side note. This formula only works if the function is differentiable, which just means no sharp corners or cusps, and if its derivative is continuous. Basically, the curve has to be smooth for this whole thing to work. Okay, so now that we have the formula, how do we actually use it? Well, I've got a simple, repeatable game plan that will work for any arc length problem you come across. All you got to do is follow these 5 steps. 1. Find the derivative. 2. Square it. 3. Add 1 and stick the whole thing under a square root. 4. Grab your limits of integration, a and b, from the problem. And finally, step 5, solve the integral. Now, that last step is usually the hardest part, but this structure really helps keep everything organized. All right, let's get our hands dirty and put this process into action. We'll start with our first example and find the arc length of a semi-cubical parabola. This is a total classic. You'll see problems like this all the time. So here's our mission. Find the length of the curve given by the function y equals 2/3 times x to the 3/2, but only on the interval from x equals 0 to x equals 3. Okay, let's follow our 5-step plan. Step 1, we find the derivative, which is just x to the 1/2. Easy enough. Step 2, we square that, which gives us x. Step 3, we add 1 and put it all under the radical. So our integrand is the square root of 1 plus x. Finally, we set our limits from 0 to 3. And look at that. This integral is perfectly set up for a simple u substitution. So after we do the integration and evaluate it at our limits of 3 and 0, we find that the exact length of this curve is 14/3. See? The 5-step process makes it totally manageable.
Okay, so that first example was designed to be pretty friendly, but as you probably already know, arc length integrals can get really complicated really fast. So let's level up and look at a couple of examples that use the kinds of algebraic and trig tricks you will absolutely need to recognize on your exams.
First up, let's find the length of y equals the natural log of cosine x. Now, here's a pro tip. When you see a problem mixing trig functions and logarithms, you should be on high alert for a trig identity that's going to save the day. And there it is. After you find the derivative and square it, you're going to end up with 1 plus tan squared of x underneath the radical. This right here is the aha moment. I mean, if you don't spot this identity, you're pretty much stuck. But if you remember that this is a Pythagorean identity that simplifies to secant squared of x, well, the square and the square root cancel each other out, and a really nasty-looking integral suddenly becomes incredibly easy to solve. All right, for our next example, notice that the function is given as x in terms of y. Don't let that throw you off. It's no problem. We just find dx by dy and integrate with respect to y. But there is another hidden trick in this one. So here's the absolute key to this problem. After you differentiate, square it, and add 1, you're left with this messy-looking expression under the radical. But it is not random. These problems are almost always designed with a clever trick. This expression is actually a perfect square trinomial. Recognizing that it collapses down into a single term squared is the whole game. Once you see that, the radical just disappears, and the integral becomes a simple polynomial. Okay, let's zoom out for a second. These examples aren't just about crunching numbers. They really show off the true power of what integration can do. You know, before calculus, finding the exact length of a random curve was pretty much impossible. Arc length is the perfect example of how this idea of summing up infinite, tiny pieces lets us measure things that were once thought to be unmeasurable. And that leaves us with a pretty cool final thought. If we can do this for length, what other seemingly impossible problems, with shapes, with volumes, even with things like probability, can calculus help us solve?